Thank you very much for the invitation, the very kind words. First and foremost, it's a great pleasure for me to be here. I named the company EMI, which exists since approximately a year after EMI Noether. So it's a special honor to be here in Erlangen, as you all know. And it's true, I now have a double affiliation. My heart beats for what can be done in engineering with the help of AI, from a, let's say, realistic point of view, and I will try to give a realistic, positive future, and trying to blend what I consider is flabbergasting and an exaggeration. And this is how we will introduce the word reference models, which is, I think, a future in engineering, which is realistic, which is doable, and which is also in the sense of a new tool helping numerics and improving the way we engineer. So the way, or the main messages I want to convey today is I want to touch about the topic of AI for engineering. So everyday processes which are data-driven, where you use simulation, where you use your numerics, and how this can be enhanced and is already enhanced by AI, which is a very different world than LLMs. And I will show why I think that reference models are the way forward. And I will also show you a few of these models we are already building. This is very, very opinionated, very much what I believe in, very much how we got also funded our company. It's my personal opinion. Opinions change over time. Don't take me too serious. Build your own opinion based on this talk. So if we go to the current situation on the AI, in the AI world, we see basically a pattern. And if I have to predict what's the next breakthroughs in 5 years, I don't know. But what I will surely know is that these breakthroughs are built on transformers. These breakthroughs run on NVIDIA GPUs, which are built at TSMC, which are built with ASML machines using Zeiss technology and Trumpf laser techniques. So this is the way our ecosystem in AI works at the moment. It's a global intertwined affair, which crazy numbers at the moment. OpenAI and Anthropic raising at evaluation of now, I think, $500 billion. OpenAI and both companies are far from being profitable. I think they are the two companies making the biggest losses per year in the whole history of humankind. But still, we are putting money in data centers and LLMs like crazy. We're building data centers with more than 100,000 GPUs. And if you actually do the math, what is the next big frontier if you build all these data centers? And that's obviously energy. And also connecting to Erlangen, Siemens Energy is the only European company stock listed which has a bigger gain than NVIDIA in the last 2 years. Why? Well, because we need so much energy for powering these GPUs. So it's a crazy world we're living in. Everyone can take their own takes on it. I think it gets wilder and wilder every year. So if you're now pitching to investors, and this is how I would start, you would obviously say something along the lines that, look, there is so much transformation happening in language, so much transformation in vision. I put natural sciences a bit out because we got 2 Nobel Prizes last year from AI, but we don't see this transformation in manufacturing engineering. And that's actually where the real value lies. I mean, most of the industry is somehow based on engineering tools and manufacturing tools, and yet this is hardly touched by AI models. So AI models are good at rewriting your emails. AI models are good at, proofreading some stuff, but they're not at the core of engineering. And obviously this is, I think, very big, where the big value proposition lies, but it also where it gets much harder to get traction. So why I'm naming these models reference models, or why I'm talking about reference models. I generally think that foundation models, we all know foundation models, so extremely large models trained on internet scale data and applicable to a lot of tasks and a lot of processes like GPT, GPT-5, Gemini, Claude, Mistral, and SEM, so segment anything from Meta. These are foundation models, and these are trained on in these huge data centers, and yeah, they work with text and image data. On the other hand, there's lots of claims about such foundation model for physics. I'm working on a paper where we actually try to derive how much it would take from a cost perspective if you try to build a foundation model which works for the whole computational fluid dynamics. So taking into account all these different flow regimes, taking into account all these different turbulence models from RANS to LES and whatever is there, taking into account all boundary conditions. And the data set was probably more than the money we have on the world. So, and that's just CFD. I don't have these calculations ready yet, but it's enormous amounts. So this claims to have one model which does all physics is probably nothing which is going to happen in the next years. I don't know if it's going to happen somewhere, but I found it very misplaced, especially if you look at the reality, which is very different, and where we see very specialized models working as surrogates, so as replacements for certain way of processes. But what I think is going to happen, and what we are betting a big amount on, is that we can build such models which are for a certain niche. For example, for weather modeling, as I will show, for external aerodynamics of planes, for semiconductors, for ejection moldings, for all these specialized processes. And you can build models which generalize fairly well and which basically offer very new tooling in these areas. It's an intertwined affair between data science, data generation, and machine learning, and a very unexplored direction. This is where my talk is mostly about. So we all know, and you know probably even better than I do, that nature is described by differential equations from all its forms, from high energy physics in the very left to astrophysics and Einstein field equations in their glory. Interestingly, if you look at these equations, it's always balancing physical phenomena against each other and solving them. And the most important part from a machine learning perspective over the last 15 years have been in the classical chemistry side, where breakthroughs like AlphaFold with protein folding and molecular dynamics in particular have really been instrumentally transformed with machine learning. Other areas, not so much yet. My expertise or my modeling is more on the fluid dynamics side, because this is very much tied to industry, and this is very much where I think the next kind of breakthroughs is happening here. One thing I always have in my head when we talk about PDEs, again, everyone knows how to formulate a PDE here in this room. It's very important to keep in mind that we cannot solve most of these PDEs analytically, so we need to discretize them. And if you write down a PDE in these formulas where you put the temporal dependencies on the left and the spatial dependencies on the right, you will have to do some discretization. And especially with these spatial dependencies, if you're in 3 dimensions, if you have higher order derivatives, the discretization of the domain, because you need neighboring stencils, neighboring mesh cells to get derivative estimates, needs a lot of meshes, and the number of the distance between those meshes gets very small. Otherwise, numerics is not converging, and so on and so forth. That is a theoretical aspect, and I didn't pay much attention to that until I saw the first time data, for example, of a Formula 1 simulation. So here, in order to run a full CFD simulation on the 3D volume of the car, I I ask the audience how many mesh cells you think one needs for doing that. Who thinks less than 1 million? Who thinks less than 10 million? Who thinks less than 100 million? Who thinks 1 billion? That's approximately the number. So we are in the range of 1 billion mesh cells, and we do this in a steady state. So we don't model the full transient behavior because we simply cannot store that. So we do an averaging. We model it. We model this steady state behavior, and this is like horrible complicated. And that's very different, a very different beast for data, especially when you talk about neural networks. Similarly, this is actually AI generated by one of my students. When you do a black hole simulation, and when you do it in all its glory, and for example, 2 black hole mergers, just doing this simulation for 10-15 seconds, you produce 100 terabytes of data. So totally infeasible that you generate a training set for a neural network to train. This is two aspects to keep in mind. And I will start now with one example where I witnessed myself the impact of AI and the transformative power of AI. During my time at Microsoft Research, starting this endeavor in 2022, we built, I would say, the first foundation model for Earth science, so for weather modeling of the whole globe. And it was approximately this time from 2022 to 2024 that we saw this transformative power as AI had in this field. I will later say what impact this has. Why weather is such a prime example, coming to numerics, because we just don't know how to numerically describe weather. We can approximate it by writing down the Navier-Stokes equation, by writing down the couples of the different weather phenomena, but nobody knows the true weather equation. So if you learn from data, if you learn from like past weather measurements, you obviously have an advantage over numerics. So this is a ideal test bed for AI, because it can understand patterns, and it is not upper bound by numerics. So first. Secondly, we have tremendous amount of data, because humankind is doing nothing more, or likes nothing more than storing weather data, apparently. And there is a lot of other data like simulations, climate simulations, all done with running these examples. So it's a very nice test bed. I think the Pangu weather moment, or Sputnik weather moment, depending how you call it, was 2022, roughly 3 years ago. It was the first weather model which outperformed traditional forecast, human-made forecast on medium-range weather forecasting, which was quite exceptional back in that time, and made a lot of people, I can tell you that firsthand, nervous. And in the similar spirit, my group at Microsoft, we were looking at a more generalizable model, which should be applicable to all sort of weather phenomena, from storms to hurricanes to the tracking, to pollution, to extreme events, and so on and so forth. And we saw the pattern the following. We saw a 3-layered process. So we had this analytical age where Navier-Stokes equations were formulated, which allowed us to describe the principles of weather modeling. We had the big numerical age, where this analytical Navier-Stokes equation were implemented and numerically discretized into a computer, and were solved and led to the weather forecasting, as we all know and love or hate them. And then we saw this AI age, and especially in the last part of this AI age, the first foundation model was launched, which is, as I said, a model which just does more than one task. And the reason why we implemented this foundation model is we saw these computational demands, so to model all sort of weather phenomena, from turbulence at convective scale to subseasonal interactions. You need a huge amount of compute to model them, which comes which generates a bottleneck. Secondly, these weather models are very complex to maintain, so there's a long development cycle, and the improvements are relatively minor. And thirdly, you hit an accuracy limit because there is only a certain approximation, and under like a resolution of 0.1 degrees, these models make approximation accuracy limitations. So there is a bottleneck in numerical weather modeling. And one slide in the middle, if you do weather modeling, you have to become a flat earther. You really have to think of the weather as like 2D images, or if you have a good imagination, 3D images, because you have the atmosphere which you stack. This is important because this is the connection to computer vision. This is very much where we have the best tools in the world, because computer vision, image recognition, image segmentation is working on such kind of data. Yeah, so why we need these foundation models? So as again, foundation model for Earth science is a very specialized foundation model. It's not the same as an LLM, because it's a generalized model, but for a very, very specific problem. Yeah, we have exabyte of data, as I already said, and exabyte is by the way, no exaggeration. We have common physics, so weather is universal, Navier-Stokes equation is universal, so there is a lot of transferability, and we have really, really compute and infrastructure demand, meaning we cannot afford for each type of problem to develop a new model from scratch. And it really, really would be beneficial to have one model which does solves all these problems together. And that's the type of such a foundation model, or as I said, reference model, because it's very reference specific. And Aurora is such a pre-trained model which is trained on a huge amount of data and then can be very quickly fine-tuned. And actually this fine-tuning, and by the way, when I talk about this project, this was already after I left Microsoft. So this fine-tuning took the team approximately 4 weeks, or sometimes 6, sometimes 7 weeks, to get a new task unlocked, getting new capabilities beyond the performance of numerical weather models. And just to give you an idea, the pre-training was done on a huge amount of data sets. So this was all these data sets from weather modeling, like ERA 5 is the most accurate weather data set we have, which blends numerical weather forecast with actual measurements, high resolution forecast, climate models, and different other forecasting schemes. And it was trained 3 weeks on 32 A100s, and this was like a generalist weather model which had understood the weather principles and how these different variables at different pressure levels behave and interact with each other. And that's very important because these three-dimensional interactions models are understanding that, even if some of, or to an extent that if you introduce a new variable, it understands the pattern depending on what it has seen in the past. And give you very briefly a few examples. The people were able to fine-tune Aurora on air pollution forecasting, a horrible complex task where no good numerical model exists and hardly any data exists, like for example estimating SO2 or NO2 concentration. And these are variables non-existing in the pre-training, because the pre-training was on the weather variables and there is no SO2 in weather. But still the model, SO2 still behaves very similar because it follows the wind patterns and so on and so forth. So the model could very easily, with only a few data, adapt to this type of problems and outperform the best human forecasts, and actually, for example, capture like sandstorm in Iraq very accurately. Obviously, this is a sandstorm which was in the past, because otherwise you wouldn't be able to compare to the ground truth. Similarly, ocean wave forecasting, again, there was no ocean waves in the data. This is very complicated data. The model was or the team was quite fast adapting Aurora to these models, to this challenge, and it captures, for example, this typhoon here in Japan. I very quickly say two more. One thing is high-resolution weather forecasting, where you predict at the high resolution, which is much higher than the resolution of the highest training data set. And again, patterns are relatively similar, so although there is not so much high resolution data available, the model very quickly adapts to that by simply changing the resolution of the input. And one of these examples is the tracking of the storm. That's like a picture from Amsterdam, where the storm Ciarán hit in 2022. And Aurora was the only model to accurately capture this storm, where all other neural networks have failed. And this is an example of why these foundation models are so important, because there is not much data of storms in Europe, especially over the Netherlands and over UK in our data set. So we wouldn't be able to get this information from a weather data set, because simply in the last 15 years there is not such a storm happening. But since the model was trained on other data sets, like climate data sets, where you sometimes go crazy and simulate climate scenarios with 4 degrees warming, you don't want to know how this looks like, but if you do that, all kind of storms are happening. So the model has seen this type of phenomena and could adapt to this high resolution, could actually look up in its internal database, so to say, how to model this configuration. So although the data, these models got presented, like all the other models from DeepMind and so on and so forth, they have not seen in the whole training pipeline such extreme events, and therefore Aurora was able to model them. And last but not least, hurricane tracking is one of the things which this model did exceptionally well. So Aurora was published in Nature a couple of months ago and was quite a success. And for me, I left this project, which I initiated, I think, in more than 2 years ago, and I had quite some time to think how to transfer these success stories to other fields, as I said, to other fields in engineering. I came to the conclusion that Aurora worked due to 3 reasons. One is the model scale. So as I said, we are flat earthers and everything works with computer vision tricks. So in computer vision, people have developed the best tools how to operate on images, how to operate in 2 and 3D images, with different resolutions. So we could use what was developed in computer vision with a huge success. For example, SAM, so the segment anything method from Meta, uses very similar architecture. So this is really, there is no difference on this architecture side. And then there is the data scale. So huge amount of data is publicly accessible, and it's very handy to use this data set. It's very well processed. And thirdly, which is not to underestimate, tasks and metrics. We knew what to optimize for. We knew how to train, and we knew how to fine-tune. This is usually quite underestimated, because if you go to a new domain, you actually don't really know what to tune your models for. And I also have to say, there is no physics-informed priors or whatsoever in the neural network. All the knowledge the model got was purely from the data. We tried, obviously, many different things. The best for this, at this scale, is let the data speak. Make sure the data is provided to the model in the right way, and make sure that the model understands what data. Because if there is a discrepancy between the data, the model will just learn to predict the average. So we now get a step further and see how we can apply this concept to engineering, and introducing these reference models which I'm talking about. So if I now have to pitch to scientists, and I do that a lot because I want to lure smart people into the company, I have to tell them, well, you know, all good, but when we want to build these models, we have to overcome challenges. And challenges is, again, there is this model paradigm, there is the data paradigm, and there's the metrics paradigm. We don't have a model which works for a Formula 1 car. There is no machine learning model you can take off the shelf and put on a Formula 1 car. It's just not possible. And what I put here in the middle is called a fluidized bed. That's a classic example, so only look at the first line of a multiphysics phenomena, which is modeled with CFD-DEM, so computational fluid dynamics and discrete element methods. You have these sand-like particles, which are these small little dots, and then you have air blown from below, which is modeled by fluid dynamics, and they interact with each other in a very chaotic way. This is a classical example in numerics to check how good and how stable your solvers are, how to model that with a neural network, how to even encode that in a neural network, what to predict with this neural network. So it was very clear for me we have to solve a formulation that we can apply neural networks to such sort of problems, similarly how we could apply that to weather. And then the next challenge is we have to think of how we actually get data in a way that we can make this model scalable and applicable to people. Yeah, so we built through a sort of through a step of papers. We built these models. I will quickly say what we did, but keep in mind that everything is transformer based. So my first prediction or my first statement, everything will be transformers in the next years. So we basically the name of the game is how to apply transformer to sort of these complicated problems. The first conceptual difference was, and this I had, I think roughly 3 years ago, when looking at these particle simulations. I looked at something very similar, not that, and I realized that you can describe that with like colors, with a field, and actually that is what a neural network is very good at. Neural network is very good at outputting continuous functions, continuous representation. A neural network is not good at outputting different particles and their interactions. So I think the most important conceptual difference is to think of everything which we're modeling as a field. As a field, and the neural network approximates this continuous field. And that works very, very well and is very, very scalable, because suddenly you're not restricted to, and on the left you see, I think this is 300,000 particles. You won't need 300,000 computational nodes to model that. You just need as many nodes as it's necessary from the degree of freedom point of view to model that as a field. That was the first, and actually that's also the way how we are modeling this. And I'm not going into detail, but we're modeling the particles as a field, and the field we're modeling is the displacement field. So at each point in space we predict the displacement, and that's nothing else than a field description. And the fluid we basically model by the velocity field. And then we need two different encoders. I'm not going into detail here. And then we basically let these fields interact with each other. And then we output also field quantities. That's why on the lower part where you see the neural network outputs, on the left you only see basically this is a fraction, the isosurfaces of the fraction of particles in a cell. So you cannot output particles because you don't have particle information, but you can output like field-like quantities.
So, but you don't write a PD, you don't write an Navier-Stokes equation or so for this field?
No.
You let somehow, you write say a transport equation, but you let the computer learn what the transport vector field will be.
A very good question. So we input the data such that it can infer field quantities from it. And it sees these particles as like instantiations of a field and outputs also field-like quantities. So you manipulate the data and you manipulate the learning task in order that you predict the field. And neural networks are very good at predicting fields. Yeah, and the second, so this is basically the paradigm, how we are modeling it, so everything is field-based. We still have not solved another problem, and this is these extremely large scales. And there is another important insight, and that is at some point, if you look at these CFD simulations, right? So when you do the CFD simulations, I let you estimate that the mesh of a Formula 1 car, you realize we're in the order of 1 billion of these mesh cells. But you actually only need these mesh cells, it's like this large number of mesh cells, because otherwise your numerics is not converging. If you redo the numerics with much coarser meshes, it's just not converging. in order to represent the full scene, the full physics to the neural network, you need much, much, much fewer points. Because the physics can be caught by well, much like the physics degree of freedom are very different than the simulation degree of freedom. That's a very peculiarity in this kind of, in many of these simulations. But still, what the neural network should be able to is to predict the full, like the full mesh, because you need that for quantities like drag and lift coefficient, which are integral over the surface, and if the mesh is coarse, this drag and lift coefficient are not exact, and that is what an engineer is interested about. And obviously, and most importantly, there is a mismatch between data, or a difference between data. In an LLM style, each word can be converted into a token, and this is what you train on. Here, you can get a lot of information out from one data point. Simply because you can think of this car, and you can sample, I don't know, 100,000 points and predict another 100,000 points. You can do that in all different kind of combination. You get a lot of different learning problem out there because the physics, the underlying physics the model has to approximate is the same. So although the data is scarce, there's more information in one of these data points compared to language. So it's a very different learning paradigm. The way we develop this and the way we approach this is also, again, with this field paradigm, we use something like which we call anchor attention. And the concept is actually pretty simple. What anchors are points on the surface and in the volume. Let's forget the volume for the time being. Points on the surface which are used for learning. So you use a certain amount of points, you input those points, the model infers the geometry and predicts quantities on the surface. Importantly, here comes the fact in that you don't need as many modeling degrees of freedom as physics degrees of freedom as simulation mesh degrees of freedom. And with this anchor point, you get the model to the best it can do. And we show in this paper very nice curves. If you increase the anchor tokens over a certain threshold, the model is not getting better. It just computation gets much more expensive. And then you use, in inference, you can use query tokens. So you run your inference on these certain kind of anchor tokens, and then you can put additionally tokens in between, and basically the model interpolates between those tokens and gives you the full simulation mesh. This paradigm switch of using anchors, which are representations of the field, and queries, which learn to fill the field, has another very important quantity. You don't need the full mesh to train. You don't need 1 billion mesh points to do a training step. You only need a certain amount of data, and that's very handy because training gets relatively cheap, and in inference you can generate the full mesh. This is, I think, was one of the breakthroughs for us. And yeah, the model, you can obviously need this. This is what you need in deep learning, very different than mathematics. You need checkboxes and red crosses to basically show what the model can do and cannot do. That's not so important. I think the important graph is this one, and I want you to look only on the left. So this is predictions of surface and volume velocity. The orange one is our model. And you see that other models at 2 million points, this is the maximum these models can do, because basically it's very hard for a neural network to digest more than 2 million points and to do something with it. But our model can very easily then, with this query mechanism, go to 16 million, go to 32 million, go to 100 million, go to 1 billion, because, well, this happens in linear scaling by just inputting these query tokens in a for loop. So this is the properties, and yeah, these models really performed well. So by the way, Domino is the most used model in industry. It's from NVIDIA. that's what you always get asked, how you compare against domino. So this is one of the tasks, how these models compare against domino. Lower is better. Domino is really not the best model in my opinion. The next thing we had to, or the next issue is the data scale. So basically modeling is relatively easy. So you have to come up with a way of having a scalable model approach which works for all kind of problems. That's handled with the field-based approach and with something like representative tokens, but data is much harder as a topic to crack because there is no error 5, no good data set. So error 5 is the data set, the big data set of weather. No good data set means, well, no good model. These engineering simulations are super costly. So we're talking sometimes about weeks or months, depending on what you're simulating. In many CFD simulation, people don't even think of using the most complicated models. They use very, very simplistic models for turbulence, for example, because otherwise it's just not tractable. So why would you produce a big data set, or how would you produce a big data set? Secondly, thirdly, what is interesting, the data is coming with different fidelities. One of the biggest challenges and opportunities, personally, I think, what does it mean, different fidelity? You can simulate a problem with different resolution, with different turbulence models, and so on and so forth. And depending on what type of problems, this can be orders of magnitude difference. And that means you can generate a lot of data for complicated simulations very quickly by low fidelity simulations. But the network obviously then also will learn to replicate these low fidelity simulations, which is then, I don't know if you want that, because this is not the actual, this is far away, there's like a sim to real gap. So you want to stay on the high fidelity side. And I think the big holy grail here is how to combine data, how to get the most out of low fidelity data and combine with a few high fidelity data. Interestingly, and every company sits on the data. So although data is the oil, companies are not very willing to share, but which is very nice because what we do, we team up with the people who write the solver software and we build our data ourselves. And very interestingly, what one would not expect, I think the biggest problem is that all these workflows are missing in most of the companies. So we are mostly talking about the problem of storage, about combining of the data, about handling different fidelities, about scaling. But actually, when you look in practice, the storage, preparing this data, loading, and so on and so forth, building a good combination of data, these type of things are missing, and that is why we don't have these breakthroughs as we've seen in weather in engineering yet. I want to show you a few of these examples we are doing. I unfortunately cannot show many of these cases all the results, but to give you a bit of an idea, one of the topics is large-scale CFD. So we are talking about power grid transformers, which are huge beasts, which convert low voltage to high voltage and vice versa. This is a classical CFD simulation, mostly heat equation, but there is many other phenomena, multi-physics phenomena going on. The problem here is that you have to make decisions practically in real time, so you have to build something which is fast and replacing the numerics, because numerics cannot do real-time estimates. The other example is, guess it, Formula One. The most appealing stuff in Formula One is from the combination of wind tunnel and simulation, because this is one of the big strengths of AI, that you can train a model on simulations, but actually really interesting is when you use this model in the wind tunnel, because in the wind tunnel you have a few slices, PIV measurements, and you can use these measurements together with the simulation of the model to infer the full 3D field, which is much more accurate than you would get with simulation or with the wind tunnel, like separately. So the neural network, which is trained on simulation, then takes the measurement of the wind tunnel and adjusts, basically, given the geometry, the inflow condition, the full flow field. And then you can, in real time, understand how different aerodynamic choices of the car impact the flow field, and always combined with measurements, and not like purely only on the computer. Secondly, I show two examples of injection molding and crash testing. These are very, very different areas. Injection molding is when you inject plastics of a molten polymer into a mold, and there it cools down until it gets a shape. Very widely used, very different equation, but very compute intensive, because you usually need to run a lot of configuration in order to get the right topic, the right configuration. Very universally applicable. Crash testing is one of these examples. Crash is basically a deformation with all the faces, so the linear face, and the non-linear face, until things deform. And the physics of the crash test simulation across car manufacturers and so on and so forth is actually very similar. So that's a place where you could build models which are universally applicable. And thirdly, this is the one I want to spend a bit more, is a project we did mostly with the university and in collaboration with the United Kingdom Atomic Energy Authority. This is plasma cryokinetic simulation. This is something which makes me extremely excited. And the idea here, or the theme here, is that turbulence, simulating on turbulence in plasma, is one of the key drivers, but also big limitations of building the next phase of nuclear fusion reactors, because it's just so hard to predict and therefore to control. It's a 3D phenomena, but in order, because you have the ions and electrons, and I is missing here in the second point, ions and electrons, you work with distribution functions, because you cannot just model these particles, and these distribution functions are 5-dimensional. They are 6-dimensional, but 1 dimension can be neglected. So they are, because the perpendicular fluctuations are much higher, happen much faster, and therefore they can be averaged out. So modeling this 5D function is computationally extremely costly, and nevertheless extremely important, because you need this. You need fast surrogates in order to understand how different effects of the system or how different changes in the reactor or in the materials affect your plasma. And we have built such a surrogate which works for 5D turbulence. It basically predicts the plasma flux. It predicts the diagnostics like Fourier spectra and different flows, and you can analyze the turbulence in full 5D, something which is not possible with quasi-linear approximations people are using so far, and which is not possible with any other machine learning methods. This is something I find extremely exciting, because it unlocks a new capability. Obviously, the topic is not solved. We still have to, again, think of how to combine different fidelities and data generation in order to make this really applicable to the practical usage. But you can see that these surrogates for plasma turbulence are not so far from being used. And what you see here is so to say the 5D. It's a visualization, because 5 dimensions are hard to visualize. So these are the 3 spatial dimensions, and on the red one on the upper part is the 2 velocity components, or the magnetic moment and the parallel velocity. And wherever you're in the phase space generates a different flux in a different velocity distribution in the spatial domain. So I leave with open challenges. For me, the biggest challenge we have to crack, and I speak now from a company head perspective, is these multi-fidelity data sets. So we have to figure out, with given cost, how can we generate data sets such that we can train these big models which are really applicable. Secondly, real-world measurements. I think where this is going in the next 2-3 years is digital twins, because machine learning has the opportunity, as I showed, to blend measurements and numerics together, which opens, well, many new doors, so you can in real time interact with your systems. But how to integrate real-world measurements, how to do that properly, is unsolved and is really open. And that already blends into the sim to real gap. It's very nice that we build surrogates which replicate numerics, but already the numerics make some mistakes. So if we, again, make mistakes on top of the mistakes, that's not good. So we have to be aware how we close this gap, how what our neural network learns is somehow reliable, but also somehow close to what is really going on. And I think the holy grail in many of these simulations is transient simulation. So if you think of airplanes, of cars, as I showed, you only do a time-averaged simulation because people can simply not store it. I think with neural networks, in future, it will be possible to train or to model the transient behavior. Because why? You simply can train in situ, so you don't have to store a full trajectory, train on it, next trajectory, train on it, but you can use a trajectory to train and then throw the trajectory away. And the neural network has the transient behavior in it. So this will open new doors, but is also a very open challenge. And I give this whole topics like 5 years. I think in the next 5 years we will see tremendous cool process here. And I also want to, again, emphasize what I said in the beginning. This is not something which is replacing numerics, physics. This is something which is coming up a new tool, which is going together with numerics and physics and opening very new directions. And this is why I'm excited about these reference models, much more than about language models. Thank you.
Thank you, Johannes. Very interesting talk. Thank you. So it's time for questions. I know there is people online also, but I don't know whether they can ask questions. But we have some, yeah, here.
So you showed that these anchor points, they are kind of located in space. But I was wondering, how do you do the positional encoding? Because that's kind of one of the most important features of our transformers is that you need some sort of a positional encoding because the position information is scrambled during the attention layers. So how do you do that?
I mean, the position is a floating number, right? And you can convert it into sine, cosine functions and use that for each coordinate. So it's very much the language model positional encoding to continuous representation.
Okay, so you just like take the coordinates.
Yeah, it happens over the coordinate. And then you have to do some normalizations because the differences are tiny and that you're in the right range and capture all the frequencies. But
Good afternoon, Professor. I would like to ask you a question. I mean, how do you see these challenges can be overcome if the industry shifts from the current semiconductor technology to carbon nanotube or a graphene industry? How would it enhance the capability of AI and all these large language models? And how do you see it?
so these challenges I put here, I think are very independent of compute, how we train our neural networks in our industry. I think these are more challenges which we have to figure out on the interplay between numerics and machine learning. How we integrate multi-fidelity data sets is a problem the machine learning community has to solve together with numerics. Same real-world measurement. So it does not really matter what hardware the simulation is running on or the neural network is running on. These are like fundamental problems those two communities have solved. Even if we, for some reason skip using NVIDIA GPUs in the future, the challenges stay.
Thank you, Professor.
I have another question. So because in the end you said that transient simulations are particularly the problem, but a lot of the simulations that you showed were transient. For instance, like the particulate matter, which was
That's a very good point. Yeah, now I have to go into detail. So the weather forecast is obviously you're right. You predict 6 hours ahead and not average over the next year. That would be bad. But it's not really transient because it's a learning problem. Like one state of the system in, the next state of the system out. And then you recalibrate based on the measurements and so on and so forth. So it's more a segmentation task kind of thing. So one thing in, one thing out. What I showed here in this slide, these are transient simulation. You're completely right, but they are much smaller scale. So we're talking here about 100K or mesh cells, and that's not in the million or even billion mesh cell. So this is what numerics can easily produce. And actually storing such a transient simulation here is much cheaper than storing a steady state Formula One car, for example. Yes, this is a very good point. And lastly, this plasma simulation, they were also transient, but they were modeled they were averaged over time. So the neural network predicted the average. So real transient simulation of this high complex phenomena, we cannot do at the moment.
I have a follow-up question there, if I may. So you also said that you are looking at in situ training, so you kind of generate a trajectory with the simulation, and then you train on it, and then you throw it away. But I was wondering if it's not even possible to only train the neural networks on a small episode of the entire trajectory, and it's similar like vision transformers, where you can show that it's sufficient to kind of train just between two different steps. Is this also something you're looking at?
Yeah. I mean, there is two different aspects. One is subsampling. The neural network the numerics need very, very tiny temporal steps. Neural networks take much larger steps because, it doesn't have to obey these convergence criteria. This is probably what you're alluding to. But then still, it's very expensive to store. But yeah, both aspects.
If I may, how do you choose the time stepping of the neural networks?
As always with neural networks.
All right. Thank you.
Yes, please. I have a question regarding how to pick the settings in which you generate the simulation data used for training. So in classical classification tasks, there are techniques like active learning which help you pick data which is most helpful for the neural network. Are you doing something similar here for generating simulation data, or how do you pick the settings?
That's a very good question. This is what normally is not asked a lot, but I think this is the core heart of it. There is no good answer to that. In any of these works or any of these reference-ish model I showed, I think it needed 20 iterations until the data set was finite. So you start with a small one, you understand what works, what not, how the model looks like, then you add more data, then you realize, oh, this is not working, then you have a design of experiment, so the parameter space, and then you step-by-step handle yourself forward. I think there is no principal way how to generate such a data set, whereas I would definitely put that as an open challenge because actually the model is only as good as the data set, and what's the best way to get such a data set fast is definitely important and very much overlooked and definitely a key component, much bigger sometimes than the model training.
Yeah, well, please.
Yeah, about how to get data, do you use like a lot of data augmentation? Like which techniques could you use for these kind of problems?
Yeah, so the data augmentation the simplest data augmentation is just that, as I said, numerics uses such fine meshes, and machine learning models can use different subsamples of these meshes. This is the simplest data augmentation strategy you can use. And then you can use all the sorts of shifts and rotates, but that's not even necessary because you get so much out from this data. Yeah.
And also in getting more data, like especially for these physical simulations between panels and so on, could data from almost toys, like something that you could maybe 3D print and play with and measure well, like potentially help when you are like in a totally different scale, like of a real Formula One car or
It's a tough question. I would rather say that it's hard. I think what goes a bit in this direction is this different fidelities, how to use a lower fidelity and a higher fidelity and how to combine them. And this is very, very unexplored how to do that. I think when people start to figure out what's a clever way to do that, then you can go even crazier and go to smaller settings and yeah.
I think Daniel, you have a question.
What do you have in model? Have you tried to optimize, for example, in the Formula One scenario, optimize the mesh of the Formula One to be more performant in terms of aerodynamics?
We have not, but that's always one of the next steps, right? If you have these models trained, you can always run these surrogates and basically play around with the input. That's the optimization loop. So you can optimize for designs, for inflow conditions, for meshes and so on and so forth. Yeah, that's the classical optimization loop you can put on top of it. Yeah.
Professor, I have another question. How do you think that new strategy like large language model can enhance better simulation?
So far, I don't see any really connection. I mean, what obviously can be done by LLM to write the simulation workflow, basically to write the meshing scheme and so on. I have not seen anything of that really working so far. I'm not pessimistic, but I think that at the moment numerics is very, like all the solvers and so on. They are very, I mean, they are 200 years of mathematics going into that. I don't see a big disruption there, to be honest. Yeah, more in the automation phase and so on. But from a pure numerics point of view, I hardly see a room for disruption.
Other questions or comments? So do you expect any maybe development related to real-time control reinforcement learning based on these surrogate models? That seems to be a promising direction.
I think so. I mean, this will, so, I mean, but building such a digital twin is complicated from three aspects. First, you have to have the numerics which somehow replicate the process, because otherwise you cannot train on something. And then you have to blend this numerics with the measurements to train the neural network, and you have to formulate the training problem that this works. I mean, this is the easier one, and then you have to do something with it, right? I mean, then you have a model which replicates a process, but then you have to build on top of it. There is not a lot of realization industry that this is going to happen. We see it experimentally and from a simulation perspective that it is possible, but I think that the industry will need a bit to adjust to this paradigm, because this is from a distance perspective much faster to reach than some AGI or some whatever models, because the tools are already there. You just need to put them together and to do a bit more research.
And so also maybe do you think, I think somehow you are pointing in this direction, right? So these models are not to be compared to the high fidelity, high precision classical numerical models for PDs developed for, as you said, 200 years. Do you think it will emerge a different way of calibrating the quality of these methods? Because somehow the epsilon delta way we define convergence, right? So in classical numerical mathematics we say, well, a method converges if given an epsilon there is a delta x, so that the solution, but it seems that this is not the right notion to, do you think there is a new concept of, in math, in analysis, in numerical mathematics that will come to calibrate the quality of these methods? Because if we keep it doing in the old way, we know that the course of dimensionality is waiting for us, right? And this is a surrogate question, a subordinate question. Do you think we will ever break the course of dimensionality?
It's a tough question, and so it depends how you use those models. So I think if you use it in a classical surrogate way, you will never be better in a way than the numerics, the best numerics you're training on, and you will never be more accurate or stable or whatever, because I mean, if you are on the axis of fidelity, this is the very right of the axis, and it's very hard to make. Everyone knows making predictions on stability and so on neural networks is bonkers. But it depends. So if you use it in a surrogate way, it's for optimization, it's for discovering new patterns and so on and so forth. You will always use it hand in hand with numerics. It's a bit different if you blend in multiple data sources. If you blend it in with real-world measurements, if you blend it in with other information of what you're trying to simulate, because then suddenly neural network can be better, whatever better means. And in that sense, I think you need to somehow also define, for example, if you talk about digital twins and predicting a trajectory over time, you somehow need to define a bit the drift, the concept drift, and so on. So these type of criteria are needed in this area. But in a classical surrogate way, I think the numerics will always be the upper bound, and it's never a one-to-one replacement, because I don't think that in the next 10 years an airplane will be made based on neural network prediction. I don't want to fly with this plane. It will be based on some engineering done from a neural network, and then numerics run on top of those.
Maybe the tickets will be cheaper.
Yes, much cheaper.
For approaches you demonstrated are data-driven. In your opinion, do you see any promise or possible applications for physics and for machine learning for such large-scale problems maybe in the future?
That's a tough question. I think for the immediate progress, the physics informed has to go into the data. I think what people are always underestimating, that how you prepare the data, how you put the data together, how you encode the data at scale is much more important than like different physics priors you put into the network. In fact, if you go very big, it's even hindering if you have like more than one loss. I think this physics-informed learning can be used in fine-tuning tasks. So if you have a very, very big model which understands these references, and then you want to obey certain sort of criteria with little data, that you can do it because the model is already trained, and you just need to fine-tune it a bit. But for training these big models, any physics-informed loss is just hindering. Yeah, I mean, it's a good question. So did we really throw that away? I mean, we have position encoding, right? So the difference is that the numerics runs on the sphere. So the simulation you see is calculated on the sphere, but projected to the plane. It would be very different if you do the simulation on the plane. Then we would learn a wrong physics. But the simulation is done on the sphere, projected on the plane with positional encoding. So the model has all the information to get the right prediction, which can then be projected back to the sphere. It's a bit machine, like the neural networks work just very differently, right? For us, it's like horrible to flatten things out, and as a physicist, it breaks your heart that you basically have an image representing a sphere. But this is the easiest way how to use these tools. You have to make the data accessible to the tools. Yeah, so I see, I mean, this is the best example, turbulence modeling. I see the generative modeling basically for many aspects. One is whenever you have a transient problem, you don't want to have a deterministic prediction, but you want to have multiple prediction that you can give an estimate of how your future looks like and how the trajectory looks like. And also these generative models, they are much more stable because the way they are trained, right, that you iteratively sample the diffusion process. So that's why we also, for all the transient problems, we're training diffusion models. And that's definitely the way to go. In these deterministic, like steady state predictions, there is not so much to gain with the fusion models. It's more a bit of the data augmentation type of thing. And obviously you can, the holy grail of getting a flow field and predicting a design, but this is very complicated because how you really output the geometry, that it is really measurable and so on. So it's really easy to make a machine learning task out of it, but something which is then actually of use is very hard because it has to fit in the engineering framework. But for all sort of transient problems, I think generative modeling is the way to go. And also in weather modeling, everyone is using generative modeling now. Just makes much more sense.
Any other question or comment? We have a few already, so maybe it's time to thank the speaker again.
Thank you.